Hello, everyone. My name is Mark Weber. Greetings from the MIT IBM Watson AI Lab for day 3 of our What's Next in AI virtual conference. Today, our theme is AI we can reason with. First, we'll kick off with just a quick 10-minute overview of what the lab is and a little bit of content that we'll set up today. And then we'll hear from our director, David Cox, to give today's keynote. Okay. Oh, first, quick disclaimer. This is my dog Lola. Hopefully you won't hear from her today, but if she does chime in the background, she's very opinionated on these topics. So every once in a while, she just wants to make her voice heard. We live in an interesting world here in 2020. And one of the things that we're observing as the year goes by is that coronavirus is really widening the corporate digital divide. And this has been observed. What this means is that the companies who are invested in digitization deeply were able to use this year to accelerate in many ways. And companies that weren't, that hadn't made those investments, were really put at a strong disadvantage when a sudden shift like this happened, such as we saw this year. This is noteworthy, I think, as we think about artificial intelligence and especially in the context of business and applications, because it may be the case that some of the investments we make in AI today don't pay immediate dividends. But we would argue that they very much allow us to adapt and get ahead of the curve so that when radical disruption or radical opportunity comes along, we're primed to take advantage of it. Some of our researchers did one of the projects that we funded. We fund a lot of different types of projects. One of them was much more focused on the economics of AI and the future of work. This is a series of papers that came out last year by my colleagues, Shubhra Das and others. And they did some really interesting work that I think helps us as we close out this three-part virtual conference. I'd like to just take a quick look at what they did and what we can learn from it and what it means for us going forward. So what they did is they took 170 million job listings and they broke those down into 17,000 tasks. And these job listings were over the course of over 10 or 15 years, I believe. Excuse me for forgetting that detail. And they used a novel task share methodology to analyze the change of tasks and demand and labor demand of tasks over time. And they did this in a uniquely fine-grained way. It wasn't just types of jobs. It was really the tasks that make up those jobs. And understanding two things. How do they change over time? How quickly do they change over time? And then how do they change between different groups, such as industry type or subtype, and also high income, middle income, low income jobs. And they found two things I want to point out. One is that as technology, information technology especially, has advanced, the rapidity of change has also increased. This is quite intuitive to us, right? They also found that these spikiness of the graph, which represents high demand and low demand changing over time for these different tasks, it can swing wildly. It really is kind of a profound visualization of a word we use a lot, which is disruption. The other thing they found is that mid-wage jobs are shifting downward. So while some jobs shift from mid-wage to high wage, actually 1 in 4 of those jobs that shifts out of the mid-wage category actually shifts down into the low wages. And this is somewhat concerning because it has implications for us that we're going to circle back to in a second. They published their findings in Harvard Business Review. Well, they published their findings in multiple places, but they summarized their findings in Harvard Business Review. And there's 3 key things I just want to share with you because they actually serve us in what we do as well. The first is in order to deal with this type of spikiness, this disruption to our labor markets, we have to commit to innovation so that our organizations are ready to take on disruptive change, whether that's, again, something like a pandemic, or if it's something like a business opportunity that is going to change the competitive dynamics in our industry. We have to commit in advance to research and development, because if we don't, we'll always be a step behind. This is also, there's also the execution component. You know, it's one thing to commit to research and innovation, but if we have hard walls between our R&D efforts and our core business, then we're never going to be able to execute on AI. And this is data showing that while 95% of companies believe that AI is a key to competitive advantage, only 5% have extensively implemented it. It'd be interesting to look at this, you know, how many companies prior to coronavirus were ready to adapt to a virtual environment in terms of cloud file systems and video conferencing, et cetera, and how many were not. It would probably be a very different chart than what we see today. And we can see, in, you know, stepping back in a time machine, that those investments might have paid off in a very different way than AI, but certainly in a profound way. Another aspect is workforce training. So it's not just about the technology itself, it's about the people who are going to be using it every day. And proximity, you know, not everybody needs to be an AI research scientist or a coder or a developer to have a familiarity with the technology, what it can do, what it can't do, so that we can make good decisions. In this case, our researchers are not just looking at AI, of course, they're looking at the industry as a whole, but in the context of artificial intelligence and how we can harness this opportunity, investing in our people is really fundamental. And ideally, not only our people that are currently in our company, but the people who will one day work for our organizations and contribute to our society. So education, again, starting early in a similar way that we wanted to invest in R&D for future returns, we also need to invest in our society, in our people who are young, in our universities and schools, because they're the ones who are going to pipeline into our organizations and make an impact. And this is really what the MIT IBM Watson AI Lab is all about on three very important levels. And it's noteworthy that, yes, we're an industrial R&D group on the IBM research side, and we need to invest in our workforce. But MIT, as an educational institution, as arguably the leading engineering educational institution in the world, is also very much at the forefront of educating our populace, and also investing in their own people to take advantage of opportunities like AI. And that's in large part what motivates an investment like the one they've made with the Schwarzman College of Computing. The counterfactual here is, you know, when tech companies come in and work with a university and end up just taking all the best people and kind of hollowing them out. You know, this is something that we were very thoughtful of from the beginning as we struck a partnership around AI research, that we want to bolster, not pilfer our universities, because this goes back to our core mission of along those, that is reflected along those three metrics I just shared. And this is where mirrored leadership really comes into play. And this is how the lab is constructed. Every project, every research project has an MIT PI and an IBM research PI, principal investigator, that is. And our directors, you know, we have a co-director on the IBM research side and a co-director on the MIT side. And I think that this type of equality in partnership is really important. So it's not just, you know, the power dynamic is such that it allows for real work to get done that's informed in both directions. And that's what we do. We've set up joint research teams. We fund, we have over 90 active projects that have been funded at different times and are overlapping with over 200 scientists. We're publishing prolifically in the top AI conferences of the world, pound for pound. I think we publish as much as any AI research, any of the top AI research groups, because we're actually quite small. And then we also welcome member companies to share in the intellectual property, to engage in that workforce training through institutional learning and proximity to this work, not only so you can do better technical work, but also so you can make better strategic decisions through a proximity to the science itself, and distanced a little bit from the marketing from some of our companies offer. Influencing the portfolio with domain knowledge is really critical, especially in artificial intelligence, to make sure that it isn't done in a way that's naive to human factors and human values. And getting support that you need, that companies need. As IBM, we're able to offer levels of support that a university isn't normally able to offer. And we're going to see some of our member companies today for business discussions following our talks, but it really has been exciting to work with a cross-section, a very diverse set of companies from many different industries. So the actions that we want to, if you're tuning in today, whatever type of organization you're in, whether you're a huge multinational or a nonprofit or a school, I want to encourage you to invest in science. What do scientific advances mean for your organization? And how do you empower your people to take advantage of those technologies and of the latest scientific work? The two have to go hand in hand. They can't really be done in isolation. So a quick recap of where we are leaving off to kick off today. We've talked about narrow, broad, and general AI, and the fact that we're on the cusp of broad AI. This is AI that's robust, transferable, explainable, scalable. And in the future, we want to move toward general AI, AI that's complex, fluid, has fluid reasoning. There's probably some argument if we want full autonomy for any AI, but on the spectrum of being able to do more advanced tasks that require more advanced levels of intelligence, this is really what we're talking about. And we've talked about AI we can trust with robustness, fairness, and really listening to people. That was session 1. We've talked about AI we can scale. We covered neural architecture, learning to learn, and transfer learning. And today, finally, we're on AI we can reason with. And we're going to be learning today about Neurosymbolic Ai, where we combine neural networks with symbolic architectures and imbue AI with a better understanding of what is really going on in a given task. We're going to talk about multimodal learning, where we're doing something humans do all the time, which is integrating different types of data. And lastly, we're going to talk about causal inference. And this is, very intuitively, from a very young age, we start learning cause and effect. If I do this, that happens. And this is how we reason about the world, is by walking around with a constant kind of almost intuitive understanding of cause and effect. And yet models haven't gotten there yet, but we are on the cusp of getting there now. So our schedule is very exciting. Without further ado, I'm going to introduce David Cox, who's the director on the IBM research side. David is a computational neuroscientist by training. I'm amazed at how many different things he actually has done in his life. I keep discovering new things every day and new expertises that he has or he has taught himself. From a very, very young age, he loved computers, but then he also found a passion in biology. And prior to taking this role as the co-director on the IBM research side, he was a professor at Harvard, where he led a lab doing very interesting work in this intersection of neuroscience and computer science. So David, thank you so much for joining us. I can't wait to hear you talk.
Great. Thanks so much for the kind introduction, Mark. I'm going to start the day off, the technical part of the program, giving you a little bit of a sort of a state of the field of AI and a little bit of an opinion on what direction we should be heading in, and particularly this idea of what we're calling artificial fluid intelligence. So just to jump in, this is a slide that Mark just showed. There's a lot of belief in AI currently. 95% of companies see that AI is key to their competitive advantage, but there actually is relatively little penetration to date of AI and to solve all the kinds of problems we want to solve. And I just want to dig in for a few minutes on why that might be the case. Now, there's no question that the excitement around AI is at a height that we haven't seen in decades. And that's really being driven by a new set of technologies called deep learning. And in 2015, Forbes, in typical restrained fashion, said that deep learning and machine intelligence would eat the world. And I think to a first approximation, this is becoming true. So this is an example of some of the things we can do with deep learning now. And it's interesting, having been somebody who worked in computer vision, for many years. When I started my career, I wasn't sure that we'd be able to do some of the feats that we can achieve now. So, for instance, here's a system from Andrei Karpathy and Fei-Fei Li in 2015, where you could take an image as an input, and a neural network, a deep learning system, would produce a beautiful natural language caption, like a man in a black shirt is playing guitar, or the image on the right, a construction worker in an orange safety vest is working on a road. And again, we take these things for granted, but this is a tremendously exciting capability, and it's really been enabled by deep learning. We live in an era where there are very few games left that humans are better than machines. Everything from Jeopardy, which IBM did in 2011, to Go, which DeepMind beat the world champion for with their AlphaGo system. There's a group at CMU that beat the world champion in poker. And IBM even has a system that can carry on a lucid debate with a champion debater. So if you like computers that argue with you, we've got you covered. And even domains like creation and art that we might have thought would be the sole province of humans, increasingly machines and AI are encroaching on that territory. So things like style transfer on the left, where you take a photograph and you can re-render it in the style of any artist you like, to systems like generative adversarial networks, or GANs, the images on the right, from a system called BigGAN, which was created by DeepMind, where each of these pictures aren't actually real pictures at all of objects in the world. They're actually the figments of the imagination of an AI system. So you can put in some random numbers and it'll generate out a beautiful photorealistic picture. So the pace of AI is incredibly swift. But there are problems, and I'll spend a few slides just to sort of show you what some of those might be. So this image, hopefully you can all recognize what this is. But if you ask a state-of-the-art object recognition system, trained deep learning-based object recognition system, what this is, you'll get an answer like this: teddy bear. And I would argue that this is probably the least teddy bear-like image possible. This is in fact a piece of modern art called A Luncheon in Fur. It's in the Museum of Modern Art in New York. But you can start to see maybe what's going wrong here. There's, the object's kind of furry and it's roughly round. And the objects that the deep learning system was trained on that were roughly furry and round were probably more likely to be teddy bears than to be a fur-covered saucer, cup, and spoon. Likewise, if we take the system that I showed you a minute ago, which is amazing and can do these amazing feats of apparent image understanding, Brendan Lake, Shimon Ullman, Josh Tenenbaum, and Sam Gershman showed this very same system some of these other images, like this one, and got the answer: a man riding a motorcycle on a beach. This one was an airplane is parked on a tarmac at an airport. And this one was a group of people standing on top of a beach, which is technically true, but I would argue misses the point of the image. So there's a sense in which, even though these systems are amazing, there's a very deep sense in which they don't always seem to necessarily understand the content that they're looking at, that they're classifying, that they're captioning. So there are problems. And if we go even a step further, the thing that really ignited the deep learning revolution, in addition to the availability of compute, and particularly GPUs, and the sort of relentless march of Moore's law, which caused there to be more compute power, also the availability of data really made deep learning possible. And deep learning is incredibly data hungry. And particularly a data set called ImageNet, which is a carefully curated, labeled set of millions of images across thousands of categories. And training these systems with this much data is really a requirement to get the levels of performance that we see. But that's very in stark contrast to how we as humans are able to learn. In fact, we don't need to see millions of images or examples of something, or thousands even of examples of something to classify it. We can just see a single example and know what it is. So I can show you this object, which you perhaps haven't seen before. And even though you've only seen it once, I can show you another example, and you can correctly identify that, yes, that's the same object in the image. I can ask you questions like, how many of the object are in this image? And I think we'd all agree that there are 2. And I can ask you, is it present in this image? And I think we'd all agree, yeah, but it's weird, right? So we can extrapolate beyond the ordinary circumstances and even reason about the appearance of an object in an unusual context or an unusual setting. And to dig a little bit deeper into the problem, with ImageNet, the other thing you'll notice about it, besides the fact that it's an enormous data set of images, it also, all the examples that come from that data set are sort of canonically posed. So these are some examples from the chairs category in the ImageNet data set. And you can see they're all kind of, sort of oriented in sort of the standard way you'd orient a chair. But what a team from the MIT IBM lab, led by Boris Katz and Andre Barbu at MIT, together with Dan Gutfreund on our side at IBM, did was to just simply take those objects that these deep learning systems trained on ImageNet were able to classify and just put them in a slightly unusual context or a slightly unusual pose. So what they did is they basically created a crowdsourcing app where crowd workers would have a phone and they'd snap pictures. So basically an instruction like, take a chair, put it in this bounding box, and put it in your living room. Take a knife, put it in your bathroom, put it in this bounding box, snap a picture. And they collected a large number of images like this. Now, importantly, we as humans don't fail to be able to recognize these objects just because they're slightly in unusual context or unusual views. We still retain very high performance. But it turns out that these state-of-the-art systems, which have been sort of lauded as even being superhuman in some cases in their performance, drop by 40 to 45% in their performance just by putting the objects in slightly unusual positions and poses. So there's a problem here with deep learning. And then in addition, as we talked about in the first session, these systems are also vulnerable to hacking. So subtle manipulations of the pixels in the image that are sub-threshold for us to be able to identify can cause a system to badly fail. So on the top is just another example of a captioning system where you put in an image of the stop sign that produces the caption, the red stop sign sitting on the side of the road. The one on the bottom has been subtly perturbed by Pinyu Chen, who's a researcher at IBM. And instead, the system makes a catastrophic error and says a brown teddy bear laying on top of a bed. So these are kinds of errors that we don't really understand yet. Something brittle about how deep learning systems are built. And you can even build these systems in the real world. So it's an example of a shirt that our team built, where if you wear this shirt, a person detector, imagine in like a AI-based surveillance system, can no longer detect that you're there. So it's basically like AI camouflage. So these are limitations of deep learning that we really don't understand. But beyond that, there's this bigger problem, and this is sort of the elephant in the room, this mantra that we've increasingly been sort of tackling with the lab, which is the problem with automation is that it's too labor intensive. And what we mean by that is the reason that we're seeing 5% and perhaps not 95%, aside from the newness of AI and the skills gap required to deploy those AI systems, is that AI is just genuinely hard to deploy. And in particular, a couple of pieces to that. One is that the world doesn't come with labels. So ImageNet scale data sets where you have thousands or millions of images with carefully curated labels on them, that's just not the norm in most of the problems we'd like to solve. The data are rarely of one kind or in one place. Typically when an enterprise tries to solve a problem with AI, the first exercise is actually a protracted data collection exercise where they just need to get their arms around all the data in the enterprise and put it in one place and find where it is and get it in the right formats. And that's a huge undertaking. Perhaps 80 to 90% of the deployment of a data science or AI solution is in fact that. And then importantly, many of the problems we face actually can't be solved just with the data that you might use to train an AI system. They require vast outside knowledge, and in some cases, common sense. Things like the answer to the question, can an elephant fit through a door? You might not find the answer to that written down in some large corpus of text. If you search Wikipedia, there might not be the text, an elephant cannot fit through a door. But we know things about how the world works and the affordances of the world, and we can reason about them and have that common sense knowledge which guides everything we do. Really the framing of this then is, most problems don't actually follow this sort of data science framing. And I like to think about it as sort of imagining that you have a river of data flowing through your business, and you build a dam at great expense. You have to hire specialized people to build the dam and then extract some value from that flow of data. Now, this is great if you're a Google or an Amazon who have huge volumes of data in your sort of core business of search or retail. But if you actually look across an enterprise, enterprise companies, the companies that run the world, all the behind the scenes of the world, there are rivers of data running through their enterprise, and there certainly are tools we can use today to get value out of those. But actually, most of the problems, I would argue 90+% of the problems that you'd like to solve with artificial intelligence don't involve these giant, curated flows of data, but rather they're more like puddles. There's puddles all over the kingdom, and they're more like one-off puzzles. So when we look at the kind of practical questions we'd like to be able to answer with AI, there are things like, how many employees have over 10 years of experience but have moved location last year? Why do we want to know that? Well, it's a specific question. We want to know it for a particular case. We're not going to ask it 1,000 times. We're going to ask it once, and we just need to know the answer. But to answer that question, we need to draw from different databases, different sources, text, unstructured data. We need to know things about what an employee is, what a location are, and that implicit knowledge needs to come into the equation. Ask questions like what factors might contribute to better output from factory A versus factory B. You need to know what a factory is. You need to understand what inventory is, people are in locations, all of those kinds of common sense things need to be brought to bear. Or asking a question like, why is our database down? Are we being hacked? Has our network been intruded? Or did somebody push bad code into production and we're DDoSing our own database? These kinds of one-off problems, you don't get huge volumes of training data to train on, because in the case, for instance, of hacking, you might get just one piece of data that you're under attack, and that's the first time you need to be able to identify it and then reason about it and solve it, and you'll never see that same pattern of data exactly that way again. So this is really where I think our call to action is, and this is going to be sort of a theme for the lab, and to some extent a theme for the day, of asking how do we get past the kind of intelligence that we have now in the sort of data science framing, where we have huge amounts of data and you train something to map from what you have to some sort of prediction or classification, but rather to move to what psychologists have actually had a term for a long time, which is fluid intelligence. And that's the capacity to reason and solve novel problems independent of knowledge from the past, ability to identify patterns and relationships that underpin these problems, and the extrapolation of these using logic. And then fluid reasoning uses inductive and deductive logic. And one of the major themes that we're working on in the lab, and you'll hear pieces of this throughout the day, actually dates all the way back to the beginning of AI. And Mark showed this picture in the first session we did of Nathaniel Rochester and the IBM 701. This is back in the 50s. And it actually turns out a bit of AI history. The term artificial intelligence was actually coined in 1956 at a workshop at Dartmouth that brought together future MIT luminaries like John McCarthy and people like Claude Shannon, together with IBMers, it turns out, including Nathaniel Rochester, who led the development of the IBM 701, which was one of the first mass-produced computers. And they sort of dreamed ahead that we would be here today thinking about artificial intelligence. Now, the interesting thing is that deep learning, as many of you know, is actually a rebrand of something that's actually quite old and dates back to this era, called artificial neural networks. And that is basically a technology that it's a nonlinear function approximator. The sort of jargon of that doesn't much matter. What matters is that it maps from some complicated input like an image, and then maps that to some kind of output that you want, like perhaps a label. So in the world of a very simplified world of a deep neural network, this is what an apple is. You sort of map from a picture, from what you have, to what you need. And these are trained on huge amounts of data. So you pair lots of examples of images with lots of examples of the labels you want, and then the system is able to learn through adjusting millions or even billions of weights to map between those two quantities. But the interesting thing, this is a major theme of the lab, and you'll hear more about this later today, there was another tradition of AI that's been around at least as long, and that's called Symbolic Ai. And in the land of Symbolic Ai, this is sort of what an apple looks like. We know things about the apple. We know that the apple has an origin, comes from an apple tree. We know that an apple is a kind of fruit. We know that an apple has parts. It has a body and a stem. We know it has properties like shape and size and color and taste. And we can bring this knowledge to bear. And this really gets to the spirit of using logic and reasoning. Not only can we learn through statistical learning and mapping, but we can also reason about the properties of an object. We can reason logically. We can reason about cause and effect. And this is really a major theme then of the lab, which I won't go into the details of today, but just to say this is, I think we think, an area of excitement where we can combine the ideas of neural networks and the great strength and excitement we've seen of deep learning, but overcome some of the strengths, some of the weaknesses, and complement the strengths with ideas from Symbolic Ai about being able to reason about properties, being able to reason about cause and effect, being able to think in structured ways and formal ways about symbols. So this is an area that I won't be able to get into today, but this is a major research program in the lab We have many different activities going on here, everything from natural language understanding to safe AI, to building generative models, like I showed you earlier with the generative adversarial networks, and even things like planning actions, optimizing code. There's really an interesting nexus here. And today in this session, you'll hear from some of the people who are leading different parts of this charge. We think it's very exciting. We think there's a lot of potential ahead for AI, and ultimately, to get to that next phase, we think this sort of notion of fluid intelligence is ultimately going to be central. So with that, I'll close, and I hope you enjoy the rest of the day.
Thank you so much, David. Oh no, can you guys hear me? Am I frozen?
We can hear you, Mark.
You can hear me. Okay. You just can't see me?
That's right.
Okay. Well, I will. Maybe my video will come up. But if you can hear me, thank you, David, so much. We're going to bring on our first speaker, or our first 15-minute speaker following David's keynote. Very, very happy to introduce Leslie Cabling, who's the Panasonic Professor of Computer Science and Engineering at MIT. She's also the principal investigator at the Computer Science and Artificial Intelligence Laboratory, known as MIT CSAIL. She's the scientific director at MIT Quest for Intelligence, so she wears an important leadership hat with the program MIT has founded, and we are actually one of the founding members of, to really motivate and create a space for students and companies to come in and work with MIT on AI. I think in addition to her research, which focuses on building intelligent robots that focus on learning, state estimation, and planning under uncertainty, I think it's noteworthy that Leslie has her bachelor's in philosophy. And before she did her PhD in the computer sciences at Stanford, she was thinking about these fundamental logic and the pursuit of truth and all the things that in philosophy we're interested in. And as somebody with a great books background myself, I'm always delighted to meet people and work with people in computer sciences that have this background, because I think as we see technologies like this play out in society, we have to think broader than just the technology itself. So thank you, Leslie, for the work that you do, the perspective that you bring. Really looking forward to hearing your presentation.
All right, thanks very much for the introduction, Mark. And so here I am talking to people I can't see, which is always strange, but that's okay. So I'm going to talk about integrated learning and planning for hybrid domains. And I should say what I mean by hybrid just to start, because actually the things that I work on are hybrid in multiple different ways. In engineering, we almost often use the term hybrid to mean hybrid between discrete and continuous, right? So that's one kind of hybrid. Another kind of hybrid is between systems that have things that are built in versus systems that have things that are learned. And another kind of hybrid is kind of high-level logical reasoning, as David mentioned, and kind of lower-level, less symbolic, more kind of reflexive behavior. So I'm interested in systems that are hybrid in a variety of different kinds of ways. Here's my motivating example. I promise you this is not my kitchen, but it's somebody's kitchen. And you might imagine that I could be trying to make a robot that could come into this kitchen and help make dinner or clean it up. The robot looking at the kitchen might really wonder, I don't know, where's the fork? Like, what's going on here? Okay, so what makes this hard? What makes this problem just really very daunting from the perspective of robotics? One thing is that the state space is just huge. Robotics people like to think about how many degrees of freedom, how many motors in some sense their robot has, and that's a kind of a measure of the complexity. But think of this kitchen. Think about all the different variables that describe the current situation, the positions of the objects, not just that. It's like the contents of the bowls and whether the stove is on. All these things are part of the state space. And so it's really big and complicated. The horizon is very long. So when we think about planning, about kind of determining a long-term course of action, generally speaking, that problem is hard, and it gets hard very quickly in terms of how long the plan needs to be. So the difficulty of solving a problem generally is exponential in the length of the plan. And another thing, a really critical thing that makes this problem hard is uncertainty. So often in robotics, if you say that you're working on reasoning under uncertainty, people will say, well, if you just get better sensors, then you won't have to worry about that. But that's just fundamentally not the case in this problem. Better sensors won't help us understand, what's in the pot that's under the cookie sheet, or whether the leftovers are rotten, or what time the people are coming home and wanting dinner. So fundamental uncertainty also makes this problem hard. I focus on robots mostly because I can have a robot in my lab, and it's a convenient domain to work on and think about. But this general notion of difficult, long horizon hybrid problems with uncertainty, these kinds of problems occur in many other situations. You might face it in a disaster recovery scenario, in construction, in logistics. So these are physical domains that have the properties that I was talking about. But actually, there are non-physical domains that have these properties too. So maybe building an agent that could help organize a conference faces all these problems. There are many variables. There's lots of uncertainty. And so the focus on robotics makes life easy and fun for me. But the things I think about, I think, can apply more broadly. So one thing I've been thinking about lately is, what is the process that we can use to engineer an intelligent system? And I'm going to just kind of lay out a space. So in one dimension, you could think about how complicated the answer is to the problem that I have to face. So if you need one robot that can vacuum one house, and you asked me to engineer such a thing, I could do that, and it would be very relatively simple and straightforward solution that I would deliver. If, on the other hand, you asked for a robot that could do a variety of things in a variety of different houses, and it could do things on demand, then that might have to be a much more deeply complicated system. Another dimension of variability that's important is what the engineers who are building the system know in advance about the domain. So sometimes they know everything about the domain, and sometimes they know very little. Down in this bottom left corner, we have kind of the classical engineering regime where we need a machine to solve a specific problem. We know what the problem is, and we apply good engineering techniques to build that system. So that's a classical thing. It works great. And when we can do it, we should do it. Over here, systems that are very complicated, but we, the engineers, understand them pretty well in advance. Those were really traditionally the realm of classical knowledge-based AI. The engineers would build a system to maybe do reasoning online, right? Often reasoning is what you need as the problems get more complicated, but we knew what was going on. More recently, there's been a focus on the case where the engineers don't know everything about the problem in advance. And lots of machine learning problems and solutions fall into this category. The problem that we're trying to solve is not highly complicated, but the engineers don't know how to write down the solution. And so we use machine learning methods to try to arrive at a solution. Now, the place in this diagram that I really want to work in is in the upper right-hand corner, where we have all the domain variability and flexibility that classical AI systems used to focus on, but we also don't really know that system very well in advance. And so we have to combine all the tools that we have, tools from symbolic classic AI with tools from machine learning, to build these systems that are flexible and rich and can operate in domains that they don't know too much about in advance. So our strategy for approaching these problems, here I was riffing on the title of this seminar, and I decided to call it Reasonable Intelligence. our strategy is to think about general representation and inference mechanisms, pretty generic ones. A good example is convolutional processing, which is what's in all the neural networks that do computer vision these days. But there are other ideas, like the idea that I'm a physical system embedded in three-dimensional space, or that objects are clumps of matter that cohere. I can build in some of these very fundamental properties of the world, and then actually use models and do reasoning over these models. And that's the way I'll build the system. So what I'm going to do is talk you through, show you an example of a system that we've built with this underlying yellow layer of kind of algorithmic and representational commitments, and also some hand design. And what I want to say about this robot before I show it to you is that any individual thing it does, like a couple of smart undergraduates could have programmed it to do in, I don't know, a week or two. But what's, I think, very important to me about this system is that it's general purpose, and that the same basic code is going to solve a variety of different problems. We never told the robot what to do, not once. We give it a high-level goal, and it does reasoning about space, about information, about its own ability to take action in the world. And but using that reasoning, it decides how to behave. So here, the first example, we asked it to put that blue box where the soup can is. And so it comes up and it figures out that the soup can is in the way. It looks at the soup can, picks it up, puts it somewhere out of the way, and then goes and gets the blue box and puts it where it needs to go. So it did that reasoning on its own. We could have put the objects in a different place. Here we asked to put the green box on the corner of the table. The green box is too big to pick up, so it didn't have to push the green box. But the orange one was in the way, so I picked up the orange one to get it out of the way. Now it's pushing the green one. It also knows that its own pushing ability is not very reliable, so it looked to see whether it went all the way, and it saw that it didn't, and it's pushing it again so that it can kind of robustly and reliably get the object to where it needs to go. So we don't always do the right thing the first time, but we try to keep going till we get it right. Here we asked the robot to leave the lab, just to go outside the door, but we put these chairs in the way. It looked to make sure that its space was free. It moves the first chair out of the way. The second chair, we thought it was going to move it out of the way too, but in fact what it does is it just grabs a hold of the chair and then brings it along with it as it comes out of the lab. So these are examples of really, I would say, fluid, flexible intelligence in complicated domains. Lately, we've been working on using machine learning to acquire the models that these systems use instead of building them by hand. And I'll just show you a quick example because we're a little bit short on time. Here we were trying to learn to pour, and fluid intelligence, right? We're learning to pour, but we pour beads or peas because we don't want water in our robot. But training, David said that data is very important for machine learning, and that's true, but data is very expensive on a robot. So here we did a lot of trials of pouring into and scooping in and out of different kinds of objects, but we had to pick up a lot of beans and peas for every single trial that this robot had. And so we focus on methods that can learn from very few examples. We can integrate what the robot already knows with what it learns so that learning is incremental. So here now, as a result of having learned how to do pouring and pushing, that's integrated with the robot's pre-existing abilities to pick things up and put them down. So now we can put the objects on the table in any way we want to, and we can say, please put stuff in the red bowl and have the red bowl be on the tray, and it figures out what to do. It moved the green box out of the way. In a second, we'll see an example. Oh, here we told it, serve some stuff in the white bowl on top of the purple blocks, and it did that. And we'll see one more example where it's supposed to put stuff in the red bowl, but it realized that the red bowl was too far over on the side of the table for it to be able to reach. So it all by itself figured out that it needed to push the red bowl over into the workspace in front of it. Here it's going to do a similar thing so that it's within reach so that it can pour stuff into it. So this is flexible, fluid intelligence, which integrates learning and planning. It integrates pre-existing knowledge from engineers with stuff that it has learned by experimentation. In 1997, I gave a talk at IJCAI And this was my conclusion slide. I said there's been a lot of progress in algorithms for supervised and reinforcement learning. So now, just not long ago, I gave another talk at IJCAI, and I used my old slide with a few amendments. And what I had, said, well, now there's really been a lot of progress on learning for supervised and reinforcement learning. But back in the day, I said it didn't really give us solutions for building autonomous agents. And I would argue that now it does give us solutions for building some kinds of agents, but still not really generally intelligent ones. And then I thought we needed human insight to complement what learning algorithms could do. And now I still really believe that pretty strongly. And fundamentally, I think the form of insight that we need for the engineering practice is to build in algorithms and data structures and really use all the tools that we have in our toolbox to try to address these problems. So now I'm happy to take questions and enter into a conversation with anybody who's interested.
Thank you, Leslie. Yeah, because of the challenges of the virtual environment, we're actually going to facilitate questions here, and I will be monitoring the chat here and looking for questions. But we'll start with welcoming back our co-director David Cox and to discuss with you. But one of the things that David said earlier, and that you kind of touched upon with this 1997 slide, is you two have been working in this space for a long time, and so you have a unique perspective versus people who are more coming into the space in the last few years with the modern and the newer resurgence of interest in AI. What is, David? When you listen to Leslie's talk today, what's an example of something where even just a few short years ago, you thought, well, wow, that might be really hard to do, or we may not get there yet. And what's been surprising, and what is also surprising that we haven't been able to solve for yet?
Yeah, that's a great question. I shudder to be in the same sentence, sort of comparing my experience to Leslie's experience, because she's obviously been a fixture of the field and seen a lot more than I have. One of the things I really love about watching Leslie's videos, and I always do, is watching the robots figure things out and kind of make funny mistakes. And it's simultaneously, there's sort of a joyful quality to it, because you almost imagine it's sort of a wayward child, kind of making silly mistakes. And some of those things are things that fit that criteria. Like I would have been surprised to see that so soon, in many ways. But on the other hand, there's a danger to that anthropomorphizing these systems and kind of putting too much of our own sense of understanding in them. So, and I think that probably has been the story of AI all along, where we kind of project ourselves onto the technology, and we think it's doing something more. And parallels like Eliza, this simple robot, computer psychologist, to today's GPT-3, where you can carry on a conversation that's much more sophisticated. I'd love to hear, Leslie, your perspective on that sort of arc of constantly resetting our expectations and not projecting too much, or maybe we should project more. I don't know. I'd love to hear your perspectives on that.
Yeah, that's interesting. As you were talking about Eliza, I was thinking about GANs. So what's interesting is that these generative models that generate some of those images that David showed us, or GPT-3, which generates text in response to some other text. What's interesting about those is that they're actually they don't have a problem to solve. They have to generate an output that's appealing to humans, and that we look at it and say, wow, that's a beautiful image, or, oh, wasn't that an interesting and surprisingly intelligent seeming story that was told. And that's a lot like having a dialogue with Eliza. You can look at it and say, oh, well, that's cool. That seems really interesting. That seems intelligent. But those tasks are really pretty different than, let's say, playing Go or even making coffee with a robot. Because in the end, it's not that the coffee making robot looks naturalistic. That's not what pleases you. What pleases you is if the coffee making robot makes you good coffee, right? So a lot of the current just overwhelmingly amazing successes of neural networks, I think right at the moment, are in problems where the objective is actually not all that rigid, and where we can interpret and be super excited about what they look like. A thing that just still amazes me is the way in which machine learning has really just completely transformed computer vision, though. It's completely transformed perception, speech, natural language, all these areas. In robotics, it is still not the case that it's easier to make a system do stuff using learning than not using learning, roughly. It's starting to creep up a little bit, but somehow the fact that the experience is so dear and that the objective functions are so hard, right? You run into things and it hurts, or you break stuff, or you spill things. That's really made that part of the field different from perception.
Leslie, I'm monitoring the questions in the chat here, and I would like to ask one on behalf of our audience members. This is actually for both of you, but we now have seen kind of almost suddenly having a voice assistant and an Alexa in your house, or is Google Home is not an uncommon thing. And it kind of, maybe some people might have predicted more societal resistance to that, actually. How many years away do you think we are to having robotics more in our house? I mean, we have vacuums, but maybe more, more helper type bots or more advanced robots. How many years away do you think we are? If I could ask you to make some sort of projection, or, what kind of barriers are there to getting there?
Yeah, so the predicting years is a game I just don't play, because I have seen that go wrong so many times.
Yeah.
But what's interesting is what the barriers are, right? I mean, I think the barrier to almost all the problems, the thing that makes a problem difficult is the variability that you have to handle. And not just the variability in the world, right? A Roomba can handle a lot of variability in the world, but it can't itself generate a lot of variability in behavior. So I think the really difficult problems, and the ones that you demand when you want a household robot in general, are ones where there's variability in the domain that requires variability actually in the behavior of the system. Because then your system has to actually perceive, understand what's going on, take appropriate action, and so on. And so it's that variability in the domain that requires variability in behavior. I think that's the measure of difficulty. Right? So Roombas are easy. The domain's variable, but the behavior is not. Factory welding robots, well, nothing is variable. But so anyway, I think variability is our index of difficulty.
Yeah, no, that makes sense. Leslie, I don't want to miss on the opportunity to ask you a question about how your philosophy background might inform the work that you do today. I can share, personally, I was never interested in business when I was younger. I showed up to a business class my first day of or my first week of undergraduate, and I just found that I could not care less about how to help Pepsi sell more Pepsis. And it wasn't until I spent a number of years, did a great books program, like philosophy heavy great books program at Notre Dame, and then worked in the poverty and development space for a number of years, that I realized for me kind of a deeper truths about business as a way of solving problems for other people. It's like fundamentally you're trying to solve problems for other people. And that's when I started to resonate with me, and then get into technology as a way of executing on that and as a catalyst for solving problems for people. So for me, my philosophy background is really what helped me become passionate about what I do today, and also inform not only what can we do in AI, but what should we do in AI, and what are the second and third order effects of that, and what are the fundamental premises that we are starting with. So that's been an important aspect of my foundation. I wanted to invite you to comment and reflect on that for a moment.
Okay. Well, so on the one hand, I do have a degree in philosophy. On the other hand, it's the nerdiest possible branch of philosophy. There's a part of philosophy that's almost math. But it's fundamentally about logic and reasoning and intelligence and knowledge. right? And what does it mean to know something? And how can I think about knowing or not knowing? And so, in fact, I've directly used stuff I learned as a philosophy major in that robot that you saw. The robot reasons using something like epistemic logic, which is like reflecting on its own knowledge and lack of knowledge, which is what lets it decide that it should get some more information. Should I look? Should I not look? So those ideas are very important. Another place where the actual technical ideas from philosophy have helped me is in the notion of reference. So philosophers worry a lot about when I say the morning star, does that mean Venus or does it not? Is the morning star the same as the evening star? Okay, so that all just seems like kind of, I don't know, philosophical wandering. On the other hand, if you ask my robot for a full oil bottle, it will go around and pick up oil bottles until it finds one that's full. And you can think of that as looking for an object that satisfies a certain referential expression. And that's how I think about it when I do that. Mm-hmm. So for me, it's not even a contrast. It's actually just a blending of stuff that I started thinking about. And here I'm just putting it into a more physical form.
That's right. It's more. It's really is a way of thinking that's grounded in a certain in logic, and I think the fact that it traverses those disciplines and for you in such a seamless way is a nice reminder for our audience and for our organizations that it's more than any one field. Being able to learn these first principles of thinking and of reasoning is really what we humans need to do for ourselves, but it also goes to what we need to do if we're going to try to create AIs that can help us and improve the world. Well, I'm going to take us 5 minutes over. We're running 5 minutes behind today, okay. But I want to make sure that we take advantage of this time. We talked this discussion is meant as a business discussion, even though we're talking about some fundamental things here. Leslie, in your work at MIT is great about engaging with businesses and startups, and I'm sure students of yours have gone on to do really interesting things. I'm wondering if you could comment on applications of this in the near term, especially, where you're seeing some of the research play out in the business world. And David, after that, maybe you can close us out. How do we think about the stuff that Leslie's been doing and the research that she shows in a non-robotics setting? How can we, you touched upon this in your talk, but perhaps we could circle back to that to close this discussion out. So Leslie, go ahead and begin if you don't mind.
Sure, I'll try. Although I have to say that I don't really know very much about the real world outside the world of academia. So that's kind of where I live. I think that some of the closest contact points for this kind of technology is in things like flexible manufacturing or construction or domains where there's some stuff is structured. So the crazy messy kitchen or the complete disaster relief scenario, that's hard because there's so much uncertainty. But things like a construction site or a container yard, there are situations where there's stuff we know in advance and we know how to build systems that can interact with the things that we know. So actually, I have one student who's been working on planning for robots that do construction by extrusion. So if I want to build a complicated structure by squirting out material, I have to plan very carefully to be sure that I don't build the robot into the structure or that it's always stable as it's being built and so on. So I think we use machine learning to help make that reasoning more efficient. So I think we can gradually build out from, the classic factory where we know absolutely everything and just gradually start relaxing what we know and building systems that become more and more robust. That seems like the trajectory, right? I don't think we're going to go from where we are to Rosie the robot in your house. So right. It's important to think about a graded set of problems in some sense.
Right. And David, IBM isn't a robotics company, and yet this type of research is very important for us. Can you reflect on why IBM is involved in this type of work?
Yeah, I think this is much more fundamental than just robots, than just industrial robots. That's not necessarily, I mean, those are interesting, and we have customers who use industrial robots, and we'd love to help them make those robots smarter. But you know, I was really struck by the thing Leslie said about how today's robots, or you know, yesterday's robots, were all about control the environment to be rigid, and then the behavior can work within those narrow guidelines. That's where we are today with AI too. It's like control everything, build a pipeline of data that's flowing, carefully annotated, build a process, work it all, you know, work all the angles to get it, this machine that does the thing, and hope that the river doesn't change course, and you know, you have to do it all over again. Just the same way if your factory kind of drifted out of spec, you'd have to go back in. So I think though, just the same way that factories are sort of contrived versions of reality, where we took the complexity and the richness of the world and crammed it down, things we're doing in the enterprise now, we're only really addressing those things that we can cram down. And the reality is that I should caveat to say that, you know, I was a professor before I came to IBM, but only been at IBM for 3 years, so I only kind of slunk out of the ivory tower and got into the real world for a short period of time. But it's been a whirlwind tour. You know, enterprises look much more like the messy kitchen than they do like factory. You know, the real world is messy, it's ill-defined. Like what we do every day, what all the hardworking people that make the world run do, they're solving weird little problems that are different every time, and they're dealing with variability. And humans are wonderfully good at that, and we're wonderfully good at that in a physical domain, like a kitchen, and we're wonderfully good at that in an abstract domain, like a business process or a product line, or you know, you name it. So I think that parallel, that's core foundational human capacity, and that's what we're really targeting. And that's why, you know, I think we can collaborate in the robotics domain, and the what we learn there will translate over into all these other domains as well. And I think that's going to be tremendously exciting when we crack that nut.
Well, thank you so much for both of you for your insight today. Leslie, it's a pleasure to get to work with you through the lab, and we look forward to continuing to support your work and the work of your students.
Thanks. It was a lot of fun. I appreciate the invitation.
Absolutely.
Bye.
Okay. Well, next on our slate, and we apologize for running 5 minutes over today, but hopefully you'll be okay with that. So our next speaker, Dr. Kate Senko. Kate is an associate professor of computer science at Boston University and a consulting professor for the MIT-IBM Watson AI Lab. She leads the Computer Vision and Learning Group at BU, is the founder and co-director of the Artificial Intelligence Research Initiative, and a member of the Image and Video Computing Research Group. Another MIT alum, Kate received her PhD from MIT and did her postdoc training at UC Berkeley and Harvard. Her research interests are in the broad area of artificial intelligence with a focus on dataset bias, adaptive machine learning, learning for image and language understanding, and deep learning. Kate, it's a pleasure to welcome you today. I've been looking forward to your talk for weeks since we first met about your work. You have so many interesting things you could talk about. So thanks for trying to boil down into a 15-minute presentation today, and thank you for your time.
Hi, thanks a lot for the introduction, and thanks for having me as part of this event. So I wanted to talk about my work on visually grounded models of natural language. And first of all, what do I mean by a grounded language model? Well, what I mean is an AI model of language that is grounded, can understand and relate language to visual perception. For example, a language model might be able to understand the meaning of the word cute by defining it in terms of other words. So if you look at the definition of cute in the dictionary, you see that it's defined as pretty. But it's very hard to describe that without any visual grounding. Whereas if I showed you this picture, I think we can all agree that this is what cute means. This is a very good visual representation of the word cute. So mapping words to visual representations and visual data is what I mean by grounding. And natural language processing models, NLP models, are becoming more and more powerful. So models like BERT, for example, transformers, they're becoming better and better at helping machines understand language. For example, Google has incorporated BERT into its search engine. And if you look at the result before and after incorporating BERT, we can see that the search engine is now much better able to understand the meaning of language. So in this example, before, it wasn't able to really understand the meaning of math practice books for adults and would return results which are books for children. But after incorporating this AI model, it is understanding that you're looking for books aimed at adults. So it's become better at understanding this linguistic meaning. And so that's great and allows us to interact with machines using natural language. But the question I want to talk about today is, can we use these powerful language models to understand the visual world and to talk to machines about the visual world? And so one of the applications, there are many applications of this technology, but one of them is in security and safety. For example, industrial safety, we may have a lot of cameras that are recording lots of video feeds from different locations, and we want to monitor the safety of the workers and also the security of the environment. And one of the difficult things about that is just the huge sheer volume of data. And of course, if you think about all the video data that's being generated out there and also within companies and in industries, it's a huge amount of visual data. So it'd be nice if we could almost do like a Google search or say something in natural language that we want to find in this data. For example, if I wanted to find all the trucks being unloaded in the past hour, if I could frame that as a natural open-ended, open vocabulary query, it would be very useful in terms of interacting with all this data and analyzing this data. Another application of visually grounded language models is in the shopping domain. So here, imagine that you have a customer who's looking for a product. Maybe I'm looking for a winter coat, and I want to be able to describe the visual aspects of that product as well in language. So I want to say that I like the results in terms of the length, but I would like the color to be lighter, and maybe I want something else to be different. So not restricting the user to a fixed vocabulary of drop-down menu of things, and just having open-ended language is the goal here. So the problem with the current language models is that they can't see, right? So you may have interacted with a lot of state-of-the-art natural language processing, either through Google search or through smart speakers, but you'll notice that none of them have cameras, almost none of them have cameras. And if they do, they're not using it to understand the visual world around them as we might like them to in certain applications. So this is still a big research problem. But on the other hand, and you might have experience with computer vision models as well if you own a home security camera, for example, and you know that they can recognize certain objects, but the problem with vision is that it's limited to only seeing a few common objects. So it's vocabulary, the number of different words it can ground, it can find or identify in visual data is very limited. So you could find cars, people, maybe buses, but if you say something like a truck being unloaded, that is something it has a lot of difficulty understanding. So that's what I'm working on in my lab. I'm working on making natural language models visually grounded and being able to, for example, take a very open-ended, natural sentence written by a human that describes an image and be able to relate that to the visual elements of the image and be able to really understand open-ended queries like, not just a cow, but a large brown or white cow and so on. So today I wanted to talk about a very simple application. Well, it's not simple to solve, but maybe simpler to understand, which is just image sentence retrieval or matching. So here, given a photo, I want to find the most similar textual description that matches that photo. So that's the first direction, and then in the opposite directions, given a caption, I want to find a photo that matches that caption. Okay. So in previous work, this was approached using neural networks, using neural network models, by taking the photo and processing it using a convolutional neural network to embed it into a high-dimensional vector space. So that's this blue dot on the right, and then taking the language, the sentence, and processing it with another part of the network or subnetwork and embedding it in that same vector space so that we have two vectors we can compare and find matches in this common multimodal embedding space. So that allows us to do retrieval. But what we wanted to look at is, can we retrieve the sentence in other languages, not just English? So can we match Chinese sentences, Japanese, German, right? So can we expand this beyond just English? Because our world is global, it's becoming more global. We have different languages being spoken. We don't want to be limited just to one language or even a few. And so this is something that we wanted to tackle. And one of the big issues with solving this problem is the disparity in training data. So you've probably heard that deep learning models need a lot of manually annotated data, and this is no exception. We need photos with captions that have been annotated for those photos. And if we look at the data sets available now for even for research, we only have really data in a couple of languages. That is a significant amount. That's enough to train a model to be accurate. Whereas, for example, in Chinese, we have 50 times less data than in English. And so if we think about how many languages there are spoken around the world and how many different markets we may want to deploy our models into, it's definitely a lot more than just a couple of languages that we would like to support. And the problem becomes annotation, right? So how do we get enough annotated data in all of these different languages? And especially for those languages that are low resource, so where we maybe really have a hard time getting enough annotated data, how can we improve our support for those languages? So that's something we looked at in a recent project that we've done in my lab at Boston University. So I'll talk about that briefly without going into too much detail. But the main idea is that we proposed a model. We called it MULE, or Multimodal Universal Language Embedding, where we want to map sentences into that multimodal embedding space. But now the space will encompass multiple languages, not just one language. So it's a universal language embedding. And then we map that universal language embedding to visual embeddings to find the closest photos and vice versa. And in the previous work that was directed to solve this problem, the way it was approached is through having a separate network for each language. So we have one for English, one for Japanese, and so on. Another approach was to have a single network, but instead of having kind of a single vocabulary for all of the languages, it had different branches of the network for each language. So we have one model, but it's separate branch for English, a separate branch for Japanese, and so on. Whereas in our approach, we call MULE, we have a single language branch, which is handling all the languages at once. And the advantage of that is better scalability. Here are some examples of our model retrieving the closest sentence for a given image in English and in German. And you can see that the top one is pretty good. The bottom one is decent, but not perfect. so it gets some things right, but it gets some other things wrong. So these are just some examples of outputs from our model. And so this was trained on 4 languages, but we also wanted to see how well we could scale to more than 4 languages. So we found more data in 10 different languages, of course, a lot less data in some languages than in English, for example. And we evaluated our model on these 10 languages in terms of image retrieval. And what we found is that whereas the previous work, you can see this orange curve. So let me explain that the x-axis here is the number of languages, right? So we have 1 language, 3, and up to 10 languages in our experiments. And the y-axis is the retrieval accuracy. So higher is better. The higher the number, the better the retrieval, the more accurate the model. And we can see that this orange line is the previous work, or competing model is getting a worse retrieval as we add more languages, right? So it does better for 1 language, but as we go to 10 languages, it becomes much worse. Whereas with our mule model, we maintain good performance, even though we're scaling to a lot more languages. However, we see one problem here that we're encountering, which is the size of our model. So the number of weights, basically think of it as like the number of neurons in our neural network is growing larger. So, and this is a problem because if we wanted to fit these models into edge devices, into mobile phones, for example, where most of the intelligence, is probably going in the future, this is a problem in terms of the size and also the speed of these models, right? So that's the problem we also wanted to tackle, which is reducing the size of the model so that it doesn't scale, so it doesn't grow so much with additional languages. And so to tackle that, we introduced a new model that we call Smaller, which is named because exactly because we wanted it to be smaller. We wanted it to be more scalable. And so it achieves the same goal of mapping multiple languages to visual representations. I'm not going to describe it in detail. I just wanted to highlight basically one idea that went into this work that improved the scalability, which is the hybrid embedding model. And the idea here is pretty simple. Basically, we only want to allocate separate parameters, separate representations for frequent words, language-specific representations. So in each language, we have some words that are very common. So for those words, we wanted to have separate representations per language. But for the other infrequent words, we basically create a single vocabulary entry for that word in any language. So we don't model them separately in each language. Right, so the idea is again, to take words that appear at least 3 times in our data and represent them separately for each language, whereas words that appear infrequently, like this word imperial, which means double-decker, is a pretty rare word, we're just going to have a single vocabulary entry for that word for any language. And what this allowed us to do, along with some other innovations that I didn't talk about, is to reduce the size of the model. So you see this yellow dot now is this new smaller model. It's called it's called Smaller. It's got a smaller amount of parameters by quite a lot. So we're using 5 times fewer parameters than our previous model Mule. And yet we're still having pretty good performance for 10 languages. So that's kind of a brief look at some of the work we're doing in this space. I just showed you this one project where we developed a visually grounded model that can match sentences in multiple languages to photos that can be used for retrieval, for example. That's one application. But we also have other work in the lab, and I'm happy to talk about that if people have questions. And just wanted to stop here and thank you all for your attention.
Thank you so much, Kate. That was wonderful. I love the baby Yoda at the end. I'm delighted to welcome Ardavan Pidram, who's currently the Director of AI Infrastructure at Samsung and an adjunct professor at Stanford University. His work is on algorithmic and architectural co-design of specialized accelerators for linear algebra and machine learning. And that work has won 2 National Science Foundation awards in 2012 and 2016. Ardavan, thanks for joining us. I would love if we could begin, if you could tell us a little bit about what you do in the context of AI at Samsung, and what resonated with you most about Kate's talk today.
Yes, thanks for the invitation. Well, I was really interested in AI in early 2000, but there was not enough compute resources, and it was like more like you were interested in the algorithms, but I was a hardware architect by training, so I approached some of the AI professors back in Iran, and we wanted to implement maybe some of these techniques, accelerate them in hardware, and fast forward, we realized everything is linear algebra. So the basic building blocks of these computations were linear algebra computations. And then since AI then was not as hot of a topic in early 2000s, so I just came to UT Austin, worked with Robert Vandegein, and on actually high performance linear algebra accelerator design. And then again, came to Stanford, and then AI had basically the sophistication of AI was supported by the hardware compute capacity. So we moved back to AI basically. And my initial NSF work was on linear algebra accelerators, and second one was actually deep learning accelerators. So from my point of view, we want to actually run these operations much faster. So we have to work with people in applications and algorithm to realize how we can simplify these computations for hardware so we can run them faster or parallelize them better. So we look at them from computational point of view, and we have to learn enough math to simplify them basically. And at Samsung, we are working on basically next generation hyperscale training architectures. I came here to basically run that project, and it started.
Very nice, and I know in our backstage channel, you seem to be really compelled by Kate's discussion of hybrid embedding. Would you like to comment on that? What was tweaking your interest there?
Yeah, so the language models, well, RNNs and LSTMs, a little bit, I believe, a little bit complicated to understand how it works, but eventually transformers took over. And there is a really nice NPR talk, I think it was by Radiolab, that talked about actually these languages having the common structure inside them. The innards of all languages have the common structure, and then basically you use the same structure to translate anything to anything. That is why we came up with all of these huge models like Megatron, and after that the Microsoft GNMPT or OpenAI, and then became Microsoft. So these language models, basically you can translate anything to anything, and then the core of them is shared between all of them. So now the talk actually went one level further than what I understood before. Very high level, by the way. I'm not claiming that I'm expert in it, but it went one level further and tried to actually compress them in a way that they fit on a small edge devices. Because from our point of view, the most expensive commodity in a hardware or system is memory and communication. So when you have chips at the edge, they have a limited memory, and if you go off the chip, you have to pay orders of magnitude more price in latency and energy consumption. So compressing these language models in a way that they could be accelerated on the edge, or actually to avoid more memory accesses even on the cloud, is significant achievement. So that is why I was really interested to see how Kate's work was trying to actually simplify and compress.
You know, it's interesting. You know, Kate, you mentioned low resource language learning, which is something that's been really of interest of mine for a few years. A few years ago, I found myself, only 2 or 3 years ago, maybe, I found myself using a Samsung phone to help me live translate with an Arabic speaking person in Africa, and it really saved my bacon. Like it was really a powerful thing to be able to like voice translate, you know, speak through a translator with a Samsung device in real time. You know, there's a little bit of a delay, but it was really remarkable to me how that I was able to converse with somebody I never would have been able to converse with. At the same time, you know, earlier this year, I was in South Africa and Kenya visiting our IBM research labs there and engaging with an organization of African entrepreneurs. And one of the topics we were really focused on in our conversations was low resource language learning, and the fact that, you know, South Africa, for example, has 7 official languages. The continent has thousands. And actually, many of those languages are structurally very different from the more predominant languages that, you know, the most well-spoken languages in the world. And there's some real concern that that they're going to get left behind, and that AI and natural language processing specifically could actually become a force of cultural homogenization and exclusion for large parts of the world that are low resource and therefore are kind of getting excluded from a lot of NLP systems today. And that's why, Kate, you know, the idea of multimodal learning with regard, like bringing multimodal aspects to low resource language learning, and especially, you know, interlanguage, but also like extra language, if you will, like where we're going to vision as well. You know, that's something I hadn't even really thought of. What do you think is, you know, if you think about this challenge of being able to deal with, as you know, low resource language learnings, what do the next couple of years of work look like, and are we going to be able to solve for that before these systems actually drive that type of exclusion that I think is threatening our society at the moment?
Yeah, Mark, I think that's a very important point to make, that we certainly don't want cultures to be left behind because not enough AI work is happening to you know, build models that can operate in the language of the culture. There's a lot of data available for European countries, for example, for North America, for, you know, a lot of English data out there. But I think we can also leverage the advances that are being made on the translation side. So there is quite a bit of work on the language translation side to support low resource languages. And I think that can help us. In fact, I didn't talk about this, but in our paper, we also use machine translation, exactly the same model that you were using to talk to your, you know, during your travel. We use this model to create basically extra annotations. So we would take a photo that had an English caption already annotated, and then we'd use the translation model to translate it into other languages, which isn't perfect, because you do lose something in the translation sometimes. But it did allow us to gain accuracy. It did give us data that was usable and was useful to improve the accuracy of our models. So I think there's a synergy there as well. And you know, on the other hand, for languages that are very low resource, you know, some in Indonesia, for example, certain places, we just don't have a lot of this online, you know, text, and especially images annotated with text. And so it's harder to create AI models that work for these low resource languages. But on the other hand, vision might actually be a bridge to help us do better at that, because, you know, if you aren't sure, for example, what an Indonesian word means, but you can find photos for that word online, you might be able to use the photo to translate that word and figure out what it means in English and map it onto the other languages. So yeah, I think that it's very important work to be doing. And I hope that we see a lot more interest in this kind of multilingual support, not even just, the 10 languages I showed are still, languages that are hugely represented around the world. I mean, like Chinese and Russian and, but there are so many other languages that are a lot less represented, but are just as important to support.
Well, we often talk about language and translation as if it was always one language at a time. And in reality, in some of the meetings we had, earlier this year, and we actually have some ongoing work on this at the MIT IBM lab. But in a business setting, let's say one of the business settings we evaluated was a financial company having a sales call with one of the customers, and there's lots of regulations about how that call can take place to be compliant, so that the person isn't getting misled or signing up for something they don't understand. And so there's legal regulations around that, and sometimes financial topics can be very sensitive. What happens in many African settings where people are multilingual, they speak 2 or 3 or 4 or 5 languages, is that they will switch languages on the fly. And there's code switching that is often correlated with emotional or sensitive topics, or sometimes with corruption. If something shady is happening, maybe somebody will switch into a different language to try to mask that a little bit, or speak in abstraction, in colloquialisms. When we think about fluid intelligence, this is the messiness of language that we often aren't able to handle, especially in low resource languages, but even among, switching among the predominant ones. So that's a topic that I'd be interested in. I'm interested in your thoughts on it, Kate. We're running a little out of time, but Ardavan, I also wanted to, maybe Kate can comment on that, and to close us out, you could also comment on the scalability of this. We talked about AI we can scale last week, and we're doing some really interesting work with Samsung on this. You mentioned it again today, but as you hear Kate say, hey, maybe we can bring computer vision into this in a multimodal way to learn language, that has a lot of implications in terms of edge device, compute on an edge device, being able to handle and recompute or retrain or infer in a live setting where you're working in this multimodal way. That's pretty intensive work to deploy at the edge, and be curious for your comments on that to maybe close us out. So maybe Kate, you could start just on that code switching challenge of when you're flipping back and forth from different languages. And Ardavan, you could close us out with your thoughts on how do we implement these kinds of things in a real world setting at Samsung.
Sure. So I think when you're talking about switching between languages, you're talking about spoken languages.
Yeah,
and that is in the realm of speech recognition. Yeah, I think that's an interesting problem. In our work, we're dealing with written language, and I think it's a little easier to distinguish what language is being spoken once you have written language, because they have different.
Well, actually, a clarification. Oftentimes, the companies that are evaluating these, it's first transcribed, and then they're trying to do analysis of the written transcription.
I see. Yeah. So then hopefully the transcription includes some annotation of what language that was transcribed in. And then, I think the problem in the visual domain becomes just being able, again, to have a model that is small enough and yet can support multiple languages, right? So if you're doing visual processing from a transcript that has multiple different languages in it, you need a model that can handle them and can also fit in whatever memory constraints you have. So I think we need even more research, because now what I showed is only 10 languages. and it doesn't include African, like I think it includes one, you know, but we just don't have the annotation, the data yet to be able to even train that model to support multiple African languages. So we need more work on that.
Yeah. And Artavan, you know, bringing these types of work, you know, models that are more fluidly intelligent can adapt between different modes of data and different languages. What's the big barrier for you that you hope to overcome in your leadership at Samsung?
First, I want to comment on what you said. It is completely true. The multilingual kids learning the both language together, but 1 year later. Like my own niece learned both languages at the same time, but 1 year she started talking 1 year later than any normal kid. So they learn both at the same time, though. And then the other one was, again, I heard something about this in another NPR podcast, which was about when you are bilingual, like we foreigners who come and learn English. If you want to do your accounting, you should learn English. You do it in English because you think more logically in a foreign language and less emotionally. So that is another thing. Like when you say they switch languages for political purposes, it could be actually for financial purposes as well, because you will start thinking more logically in the foreign language because you learned it with logic, not just like inherent. So talking about that, what Kate said is completely valid. It reminds me of how hieroglyph language was actually translated into English with tablets that they found, and they started like filling the gaps. And a lot of the stories, all the stories from like the first story in the world, the Gilgamesh story, was actually also used several Babylonian tablets, and there were some missing parts that they had to fill the gap with different tablets that they found of the same story in different languages. So using images is an excellent idea that actually we have been using to retrieve these older stories that have been lost due to disasters, wars, etc. So in terms of hardware scalability, I believe training still is so complicated that should happen in the cloud. So what we mean by a scalability is actually a scalability in the cloud, because the number of actually parameters is so huge that they don't even fit on a normal like if you had abundance of computation, you couldn't still fit it on one node. You have a lot of these supercomputing HPC problems have no other choice but to have so many nodes, not because of computation, because of the memory. Like every CPU has a certain address space. It cannot address more than, for example, 256 gigabytes of memory. So if you need more than that, you have to have several nodes. So each of those CPUs, for example, be able to address their own chunk, and then the whole problem can fit on a supercomputer. So a lot of times a supercomputer is actually just used because the problem doesn't fit on the node. So imagine that we have so much data, as Kate said, and we have also so much compute. How do we handle this? We have to actually add, as we said, accelerators on this supercomputer. So we are fighting two battles. First of all, the first battle is the abundance of data and very slow communication. The second battle is actually abundance of compute. And then in our basically all of our colleagues and all the companies, we try to actually use hardware acceleration for computation, and also like cloud computing for fitting this data. At the edge, you want to do fast and low latency computation. So that is a different beast. Like we are fighting two battles in two different fronts. One of them is to make training faster and also more scalable with abundance of data. The other one is to make the inference as fast as low latency and as low power, because your hand will melt if you have more than 5 watts or 10. I think it's 5 watts power consumption on the chip on your Samsung, for example, phone. So you have to have low energy consumption, very power efficient solutions, and low latency, and also be able to fit the problem on that small device. I mean, small device still has a lot of memory, but as you can see, we are fighting two different battles, and one of them is training, one of them is inference. Each of them has its own problems. So any solution that comes along, people try to actually adapt them for the two different sides, while paying attention what is going on the inference, for example, side. We want to train our networks and prune them so they become smaller on the inference device, and also want to make our training more scalable and also more adaptable to bigger data. What Kate is suggesting to do, like with these images, most of these should happen actually. The data retrieval could happen from the phone, but it has to probably done on the cloud, because training neural networks is just not with sample one. You get one new sample and then magically you train the network. You actually have to go over all of these new data and put them in perspective with the rest of data that you had. You cannot just update your network with one new sample, because it will just bias the network. So, so we have two battles to fight: size of the data, amount of computation, and also on the other side, latency and power efficiency.
And for those of you who are tuning in today but missed our previous sessions, I encourage you to check out AI We Can Trust, where we talk about robustness, and AI We Can Scale, where we talk pretty explicitly about neural architecture and pruning and other aspects of what Artaban is touching on. You know, all three of these go together. You know, fluent intelligence is maybe the objective, where we want to have this higher form of intelligence where we can adapt and interact with in a complex and messy world. But there are real scalability implications of deploying that type of intelligence. And part of the scalability challenge is also robustness, so that we don't have to train and retrain and retrain and retrain, and so that we can actually have devices that are stable, or models that are stable at the edge. So this was a great discussion. We're now 15 minutes behind, but it's been worth it. I really appreciate your time, both of you, and good luck in your endeavors at Samsung, Artaban. We're here to support you. Kate, delighted to be able to support your work through the MIT IBM Watson AI Lab. Thank you.
Thank you for having me.
Okay, we will keep moving, and I apologize that we are behind, but these talks, there's just so much to talk about, and these scientists we've queued up today are just are really doing interesting work. So thank you for your patience today with our schedule. Next up, I have Davi So, who is a principal research staff member at IBM Research. He manages the Biomedical Analytics and Modeling Group within the Center for Computational Health at IBM. And he focuses on the application of AI to various problems in healthcare, including explainable disease progression, modeling, and treatment effectiveness research with causal inference. So this is an intentional and great setup we've given you, Davi, with a causal inference presentation by Christian beforehand. And you know, we talked about it in a customer risk setting, and we talked about you know, how we can think about this in a dynamic environment. And very excited to see how you can take us forward with a healthcare setting. But I think we'll find that this, you know, even as we look at the healthcare setting, that we can generalize some of the work that you're doing to many different types of problems in our world. So thank you for joining us.
Absolutely. Thank you, Mark. Yeah, as you can see, actually the title of the presentation, Situation Awareness Using Counterfactual Simulation to Improve Decision Making, does not explicitly talk about healthcare, but we intend to illustrate the content by using some healthcare scenarios that we've been using to develop, you know, being part of a healthcare research department. So I'm going to start this talk actually with I guess somehow provocative, maybe not to all of us, statement that says that while intelligence as human allows us to take decisions, actually I would claim that we struggle mightily. Humans struggle mightily and are quite often very uncomfortable in the decision-making processes. How many of us have been in a situation that's pretty much, you know, with a nice metaphor with the picture that's on the left side, where we feel that like we are, you know, in the middle of a railroad intersection, very, very complex junction, and uncertain about the right action to take because we don't know where this would lead us, what the outcome would be. So, and the other point that most of us are aware, and this is so true in healthcare, is that this problem has been recently exacerbated significantly with the information overload. There's a very provocative title here from that Harvard Business Review article that talks about death by information overload. And in healthcare, it's absolutely true. There's been a huge focus on digitization, the emergence of electronic health records. If you go into intensive care units, as you're going to see a lot of the examples that we have are coming from there. It's heavily instrumented, lots of benefits from those devices, but there's also the other side of the coin, which is obtaining too much information that can often lead to confusion and suboptimal decisioning. For instance, in critical care, there's a very, very important problem that's called the alarm fatigue, where nurses are actually shutting off the alarms of the patient monitors because these things just keep beeping, and it just creates a lot of confusion. When we want to make decisions, we want to have a clear mind. So situation awareness is actually a principled approach to good decision making, and it actually stipulates that good decision making needs three things in order: the ability to perceive, so perception, comprehension, and projection. So perception is all about being aware of the environment in which we are so that we can be effective in our decision-making process. As you can imagine, it has a lot to do with sensing in a very, very generic way. The second step is comprehension. While we can observe, get a lot of observations from our environment, we need to be able to comprehend. We need to understand, what does this mean? What is this, so that we have a good grasp of the situation that we are in. And finally, the last step is projection, which is it's all about this ability to imagine future states. If I were to take this action, what would the future look like? So situation awareness mandates a principled approach to perception, comprehension, and projection, and that can lead to decisioning. As you can see in this diagram, actually, the decision-making process itself is outside of situation awareness. So after that, once this is well done, then someone can actually weigh in on the different decisions, so that can lead to the performance of an action, and the action obviously would have an impact on the state of the environment. So then we are in that never-ending loop of decision making. Situation awareness has done wonders. It's quite often attributed for safety in aviation. It's being used actually to control trains, nuclear plants, very, very heavily used also for strategic and tactical planning in the military space. And last but not least, also in healthcare. It's been mandated in healthcare. And there's actually an interesting paper here that I'm showing that appeared in the Joint Commission, Journal of Quality and Patient Safety, where they talk about situation awareness, but they also stress that it's really important not to over rely on automation. And they talk about the concept of cooperative automation, which is about that symbiosis between the human and the machine to really bring proper situation awareness in decision making. When we look at now, if we flip the coin a little bit and we look at AI, when we look at AI, decision making in AI, belong mostly in the field of reinforcement learning. And so on this chart, what we've done here is we try to pretty much frame a reinforcement learning problem within the situation awareness, if you want, framework. And so here you have what's circled in yellow, an AI agent. An AI agent, a reinforcement learning agent, does actually perceive from the environment. And there's, we learn neural network structures when we use those deep networks, like the DQN in the DeepQN, architecture, to really comprehend the state of the environment. And we use that, and there are various techniques using Markov decision processes to estimate future rewards, and that can lead to decision. What's interesting is that reinforcement learning, actually the output of an RL agent, is actually a decision itself. And then obviously someone would have to actuate on that decision that leads us to the performance of the action box. So as in healthcare, so perception in critical care, perception, you can envision, the instrumentation of those ICUs with lots of patient monitors that gives you lots of information on the patient. And then you can have an RL agent that will tell you, in this case, it will tell you which drug you should administer and at what dosage. So the two-dimensional grid that you see at the bottom right of this chart is meant to illustrate that an RL agent properly trained may may be able to tell you that for this specific patient at this point in time, we recommend to use drug number 3 here, counting from bottom to top, and at this specific dosage here. So that being said, RL, one key result that we have is that we notice that RL can be actually very unstable in healthcare, specifically in critical care areas. And this is a work that was just presented earlier this week, and actually was very well received in the medical informatics community, and as a winner of a distinguished paper award at the AMIA, which is AMIA is the American Medical Informatics Association annual meeting, which is I would say the premier meeting in medical informatics that we have every year. So I'm going to take you just through a couple of results that we have seen. So deep RL in critical care is actually very sensitive to various things. It's not very robust, and that's what that paper actually talks about. So the first thing is that using again the same type of grids, and in this case the action space is telling you whether you should what are the dosage of vasopressor, which is a type of drug that controls the blood pressure that should be administered, and also how much fluid you want to give to your patients in order. And the goal here is to control the blood pressure. So the reward in this RL setting is to control the blood pressure of the patient. And what we notice is that just by changing, slightly the architecture of the neural network that we use, the deep neural net, into this RL setting, we get very, very different, policies. That we see that the agent is going after so many different policies. This grid is meant to tell you, the color is meant to tell you whether a policy was heavily followed by the agent or not. And the first one is what the physicians are doing. So you can see by just changing slightly the structure of your neural network, you get different results. And we've done other work. Another work that we've done is we changed the structure of the reward function. What if we are more about instantaneous reward, let's say at discharge time, or much more longer term reward? So we have that variable C in our reward structure that allows us to control that. And as you can see here, you get very, very different policies. And I mean, there's more in the paper, more unstable behaviors that have been observed with the way you bin your events, the way you choose your hyperparameters, and so on and so forth. So given that, so we decided to take a step back. So instead of using what I just told you about, using a narrow setup where you pretty much have the agent telling the physician, this is the strategy that you should follow, why don't we take a step back? And we decided to bring the human back into the loop, into the decision loop. So that's really the contrast between the two diagrams that you see here, the one that's on the left and on the right. If you see the one on the right, the human is, first of all, the one on the right, we decided to limit technology to just situation awareness and not to the production of the optimal treatment policy. And we decided to put the human back in the loop there. And this is and we came up with this concept of a counterfactual simulator. This is a system that does not tell you what is the best treatment plan that you should follow, but it allows you to play what-if games. So now by putting the human back into this loop, the human is able to ask the counterfactual simulator, what is the effect outcome that I would see if I follow, let's say, an aggressive fluid resuscitation strategy? And then the system will tell you, well, these are the outcomes that you can get. So this is encapsulated into something that we call internally GNet. So GNet is a counterfactual simulator. So it is generic. We've been using it in critical care, but it is generic. It's a very generic deep learning framework for counterfactual simulations. It allows end users to test actually hypothetical treatment strategies, and by that, for each strategy that you put into the system based on what the system has observed from your patients, you get counterfactual outcomes. And it is very, very well grounded in a causal inference technique called the G computation. So for GNet to work, though, I mean, there's no secret. There is a very important statistical assumption for the G computation to work in general, which is typically you have different types of variables that play into these counterfactual settings. You do have observations, which are the L's here. This is everything that you observe on the patient, the blood pressure, the heart rate, and so on and so forth. You have treatments or actions that you want to take. And you also have things that could actually create a lot of problems, which are your unobserved covariates. It's very difficult to, I would say it's actually impossible to observe everything. So there will always be some unobserved aspects that might be in the environment that your GNet algorithm may not be aware of. But GNet will still work as long as these unobserved covariates do not have an influence on the actions. So as you can see with the causal graph that's at the bottom, the U variables, which are the unobserved covariates, none of them are pointing into any of the A's, which are the treatment or the actions. So under these assumptions, you can GNet, you can guarantee, there are some statistical guarantees that you can make. So we've been testing it, and we have some very interesting results, much more stable than what we've been having with state-of-the-art reinforcement learning approaches. So first, it does accurately estimate known patient trajectories. So this is what this diagram is telling you, where using after time step around 32, we compare the output of what GNet produce with the red one, which is what actually happened for that patient, and it does a very good job at estimating the trajectory of the patient. And also, what's also interesting is that GNet also can accurately estimate individual simulated counterfactuals. So as you know, counterfactuals are never observed, which is one of the challenge when you build this type of systems. But in this case here, you have two patients. Patient A, GNet has observed the data, and then at that junction here that's shown with the dashed line, the vertical dashed line, we tried two different treatment strategies, the green one and the blue one. One might be heavier on the fluid resuscitation, the other one might be using more vasopressors. And as you can see, the same treatment strategies, GNet is able to give you these counterfactuals, and it's allowing you also to give you personalized counterfactual for different patients. So for patient B, for instance, you can see that the result that you're seeing here is that G1 is actually much more effective at boosting, GC1 is much more effective at boosting the blood pressure for patient B. It does not work as effectively on patient A. So it allows the physicians to start playing these games that we believe are really essential for proper decision making. So the takeaway message of this presentation, and I'm going to close with this, is to go back to that finding that was published, within the John Commission, is to stress the importance that, we want to automate decision making to make it as easy as it is for us. However, this concept of cooperative automation is clearly very apparent in what I just presented, in a sense that we do believe that it's very important to make sure that the human is still involved in the decision-making loop, so that we can really help them with this information overload that leads to a decision overload problem. So that's what we had. So, and again, the GNet is a counterfactual simulator that enables this cooperative automation. And that allows us to circumvent, these issues that we had with reinforcement learning. Thank you very much. I'm going to stop here. Mark, maybe I'll pass it back to you.
Thank you so much, Tavi. A wonderful presentation, and to join us for discussion, we welcome Dr. Tianying Hu, who is an IBM Fellow and Global Science Leader for our AI and Healthcare at IBM Research. Dr. Hu is responsible for working across IBM Research to define and drive AI science leadership in healthcare. And in addition to her leadership role, leading the Center for Computational Health, she's also an accomplished researcher herself, holding over 130 peer-reviewed scientific papers and 35 patents. So thank you, both of you, for bringing your expertise today. Tianying, what resonates with you about this particular work and what it means for IBM and serving companies around the world with causal inference-based work like this in applied settings?
Thank you, Mark. Yeah, so one of the things that that we really strive to do in our computational health research in IBM is to identify areas and work in these areas where AI can really make a difference in improving the quality of care. And addressing information overload in decision support in clinical settings is one of these areas. Now, one of the things that makes this particular situation stand out against other decision support scenarios is the high stakes here, right? So avoiding unintended harm is of paramount importance here. And that's why it's really important to have this approach to keep the human in the loop and to have this approach of cooperative automation. Now, it's actually easy to see why this form of situation awareness is important for the scenario that Dabi described, which is in ICU settings where the physicians are constantly bombarded with signals coming from multiple sources, while at the same time very often have to make very quick decisions. But this kind of technology actually is equally important in many other point-of-care decision support type of scenarios in clinical care. And this is because in the real-world setting, most of the time, the clinicians actually cannot find clear-cut guidelines backed up by clinical trials that matches exactly the patient and the situation at hand, right? And so that's why it's really important to have this kind of counterfactual simulation and decision support for many of these situations. So besides these, the counterfactual simulation work that Dabi described, we actually do have a lot of other efforts addressing this kind of situation as well, including going from extracting and summarizing information from electronic health records and other sources of information to identify patients who have similar situation and trajectory as the patient at hand, so that we can form this notion of precision cohort, and then analyzing that cohort, again, using causal inference methodologies, we can then provide information to the clinician of the kind, for example, this particular intervention works better for patients like this, right? So these are just some of the examples, and we continue to work with clinicians very closely to identify what are the other areas where we can work on using AI to help them do their job better.
Yeah, it's a great source of pride for me, even though not being a healthcare expert myself, it's a great source of pride for me that IBM and IBM Research are able to work with people who are saving lives every day and to help them do that better. But it also, something that you said, I think is really important as it speaks to kind of the core identity of IBM specifically as one of a number of AI companies, is that we really specialize and want to specialize in mission critical settings. These settings where a move fast and break things approach will not cut it because the stakes are too high and people's lives are at stake, or the financial system is at stake, or a factory is at stake. These things. The easy way is to take any number of open source or off the shelf methods and throw it in and see what happens. But when we have a much higher threshold of responsibility, then it requires investing in this type of fundamental work to figure out how do we get systems that are more fluidly intelligent, deployable in a way that we can trust to do what we need them to do, which is care for people or execute some mission critical task. Dabi, you mentioned perception, comprehension, projection as the basis for decision making, and those all kind of interplay with one another. I think oftentimes we, especially in kind of a statistical sense or a deterministic sense, we can fall into an overly simplistic view of the world, and even in cause and effect, it's like, okay, X causes Y, and we lose sight of how difficult each of those are. Perception, if your perception is wrong, it affects your comprehension. If your comprehension is wrong, it affects how you project yourself into the world or project the ideal state that you want to achieve in the world, and ultimately all of those cascade into decision making that can go awry, or can support what we want. And I think that the idea of a counterfactual simulator is really compelling, because again, it's something that we do all the time, every day, as we engage in the fluid intelligence that we have as human beings, where I'm not only weighing what I think is going to happen, I'm weighing it against the opportunity cost of counterfactual, or of based on what it is that I want to pursue. And I'm just curious, how do we, in a healthcare setting, you've given a very nice presentation of that, but how do we take that forward? How do we take that forward so that we can use GNAT for many things? What's on the horizon for a simulator like this, and what are the barriers, actually, the technical barriers, to being able to use this effectively that become new research threads?
Right. So, I mean, lots to say on your question. I think one of the first thing that comes to mind is, I also talked about that symbiosis between the end user and the technology. I think in each of those segments, and definitely in healthcare, it's really important to understand how such tool will play into existing workflows, so that people can effectively, how would this really support decision making. On the more technical front, I think of the three of perception, comprehension. I think projection is probably the one that's the most mind-boggling, at least to me, because that's something that humans can do well, because we have the sense, we are able to imagine.
Yes,
we have imagination, and imagination can be triggered with so many things, our own biases and so on and so forth. So, instructing, an agent to help, humans in that step, I think this is where there's lots that needs to be done. But clearly, causal inference counterfactual simulation is a great step forward with those algorithms. And this is where I see a little bit of a demarcation between, I would say, I don't like the word traditional, but what we do in AI. In AI, we're very good at predicting things, but the concept of projecting is slightly different and nuanced. And this is where I see lots of challenges. And to another level, that assumption that I talked about, that statistical assumption that you can pretty much observe those unobserved confounders, this is what's the biggest issue that we are facing with. This ability to cope. How do we tell system to make decisions? Humans, we do that. We do take decisions in the presence of uncertainty, when we don't know some of those variables. But how do we teach a computer to do that? That, I think there's lots of work that needs to be done in that front. And which is why I think it's really important to keep the human in the loop. I don't think, it has to be a symbiosis between between the human and the machine. It's a conversation in a way that we have to enable.
It's very interesting in the context of the modern advances in generative modeling to think about AI imagination and projection, right? But a lot of generative modeling is trying to actually match a distribution that we might expect. If we want to create a hyper-realistic image of a person, we want to try to really, it's a little bit of a copycat game. Like, it's generative, but we're also trying to match a certain distribution, right? And it's true that even, imagination may have some constraints depending on the setting, but when we're trying to do scenario planning and strategic planning, and we want to imagine different states of the world that may not match distributions of the world that we've seen before, right? Where this becomes, as humans, this becomes a way that we generate our own training data, right? And it's interesting to think about what you said in projection, both in terms of informing decision making, but also in terms of reducing the amount of data that we need to train and make the inferences that we need to make, because we have some sort of imagination capability that generates that data for us.
Right.
We actually did an experiment with that last year in a construction setting where we were trying to tackle the challenge of, can we look at a half-completed building that's under construction, and for the first time, and having never seen that building before, can we infer how complete it is? And this really, in the experiment that we ran, it involves using the blueprints of the building, the way that it was designed to, what it was supposed to look like, to generate training data of, like, imagine what the building should look like in a real world picture, and then compare that to the picture that we're being asked to make an inference about. And it's interesting when you bring that into a more of a decision-making context, as you said, in a situational awareness context. How do we then do that in a much more complicated environment where we have lots of different variables to consider, right? And Jianying, I'm curious, you have a view of the healthcare portfolio at IBM Research that is, you can see kind of a large swath of things. I see these hyper-specific projects that we're funding. You have a broader view. Can you help us connect some dots here? Where are you seeing healthcare and AI in healthcare going, and how does this type of work play into that?
Yeah, so a couple of comments that I would like to make in the context of the topic that we're discussing here, right? One is another important aspect of bringing, G computation work and any other work forward in terms of actually applying it in healthcare setting is really careful evaluation, right? That goes of these models, that goes beyond just accuracy and goes beyond even, population level confidence interval assessments, but really dig into what are the potential failure modes. What's the sensitivity? What are the factors that could trigger, unintended harm? And that's the work that Dabi described in the paper that we have recently published, really analyzing very carefully how deep reinforcement learning behaves in healthcare setting and what are the factors that could cause unintended harm. And clearly the fact that this won the Distinguished Paper Award in this conference shows that people really care. This is something that really resonates with clinicians out there. They want to understand what are the conditions under which we can trust this model versus not trust this model. Right? And that's one of the really important things to address in order for us to actually apply these models in clinical setting. Another thing I want to comment on is tagging on to what you were talking about in terms of using generative models to also address the lack of data that maps to real world conditions, and also, how do we sort of reduce the reliance on the large amount of data? One of the reasons why we very often require a lot of data is because of the large search space that we need to go through to come up with the right model. Now, one way to reduce that, and this also ties into what you were talking about, is to actually pulling mechanistic models, right? That reflects the way the world operates, the way our bodies operate, right? So combining that with a statistical model, that's another way of really, in some ways, setting boundaries for the statistical models to search within, so that you can actually come up with solutions. And besides reducing the amount of data that's required to train models, this also has the added benefit of leading to truly interpretable and explainable models, because what you're coming up with from your statistical machine learning models actually is grounded in framework, right? Scaffolds, if you will, that's coming from the actual mechanisms of the world.
Actually, along those lines, I should mention that the GNet in critical care, the one that we are using now, has been trained actually using data from a mechanistic model from our colleague, our team members from the MIT. They have a cardiovascular simulator, because how do you observe counterfactuals? So that's what we use. But to Jianying's point, even beyond that, I think I could not agree more with the need of bridging, the data-driven with these mechanistic way. There's so much knowledge that's out there, especially in healthcare, embedded into those models that can give you explainability and so many other things. And that's another frontier that we hope to cross very, very soon. Yeah.
Very good. Well, that's all the time we have today. Thank you to both of you. For our audience members, I apologize that we haven't been able to get to all of your comments and questions today. You know, we're on such a tight timeline. So I want to encourage you to find us on Twitter or any social media platforms. Reach out to us through the IBM Research or MIT IBM Watson AI Lab site. You know, we're very happy to engage with you, and we hope that you've enjoyed this session and the others. So to close us out, again, thank you guys. I'm gonna bring on our MIT director Aude Oliva for a closing discussion. Welcome back, Aude. For those of you who haven't met Aude yet, Aude is the MIT director of the MIT IBM Watson AI Lab and the co-director of MIT Quest for Intelligence, which is another very important program and initiative at MIT to create a space for students and companies and to not only do core AI research, but also to bridge that to real world applications. So thanks for joining us, Aude. It's been wonderful to spend time with you on this channel, on this public channel, to listen to these great talks and to get your thoughts on it.
Thank you, Mark, for inviting me back again. It is a very exciting time, and this morning session was really amazing. I will always think and relate to how humans think, the human brain and so on. That's something that I do due to my training. And listening today, it's kind of obvious that the AI and the machine learning method developed out there are going to implement a very different type of reasoning, very different type to find a solution. And we talk about causality between events, or we study cognitive psychology to see how kids learn causality and so on. But we might discover that those statistical methods will implement causality or be able to implement causality in very different ways. And they might actually show us how to make logical arguments that might really be things we did not think of. So currently, all the machine learning methods are based on learning from historical example, the past. By their nature, those systems are a mirror of the past. And this is where what we call one-shot learning, I believe, has a lot of potentiality. So one-shot learning is what we do all the time. So we are able to change the past learning, the rules and the behavior after one event or a few events of a kind. And we do not know how to implement that the right way, at least in the current machine learning system. And something that is very true about the human brain is that every single event is a one-shot learning. Our brain are neural networks which never ever see, hear, or touch the same thing twice. It may look alike, it may feel alike, but it's never ever the same thing twice. It's always new. And so we have out there this neural network that is learning. Everything is always new, and it is more or less similar to things you have learned or heard or touched. So beside causality, intelligent system, I think, should learn about analogy, abstraction, and what is alike as another way to do reasoning and behave in an ever-changing world. And analogy is something that can be implemented in space and time. For instance, like in language, of course, like a teacher is to school, like a surgeon is to hospital. Those sort of mental space of relational similarities might be another way to get some good causality being learned.
Yeah, it's interesting as we think about, I think there's different modes with which we construct our internal causal graph, right? Mm-hmm. Sometimes it's through repeated interaction with something. It's like, okay, I've done this a number of times and this is always the result. So I've learned that in that sense. But we also draw our internal graphs through instruction. You know, if you teach me something, if you say, this, and I trust you. Like, you can assume that for a second. So if you say, hey, this button turns on your computer. Okay, I learned that once. I now know where to press to touch, to touch that. It's more similar to a rules-based system than maybe one that is just kind of we're on our own trying to learn everything, right? There's a combination of instruction and self-teaching that we do as humans, and I would say we rely heavily on instruction, and we depend on it. And sometimes we find out that the instruction we received was wrong, but maybe we have to learn some lessons the hard way as a result. What do you think, Ode? The word hybrid comes up a lot. We have like a hybrid neurosymbolic system. We have hybrid cloud. We have hybrid embedding that Kate touched upon earlier. How should we think about this word hybrid, where we're not all or nothing on any one type of modality or structure, but we really are trying to integrate and take the best of both worlds? How do you think about this in this intersection of neuroscience and computer science? Is that what we humans do at a biological level? Is something closer to kind of a hybrid approach, or is it one or the other?
I think every time you put things that are different together, you create a space of creativity and new ideas and things to unfold. So the brain is a collection of biological tissue. They are called neurons. And we are able to have abstract thoughts and follow instruction and come up with new ideas. The way those emerge from the spiking of our neuron, we don't know, but we do it. So there is a machine out there called the human brain, which has implemented what we call symbolic reasoning and some of the older AI path into the biological way to think. So we don't know how, but it's there. So I'm always very open, and I like when new ideas come together from very different sources. So the term hybrid is an attempt to put together things that originally might not have been thought to put together, like the deep learning and the hierarchical structure. And we do see certainly in a lot of the work being done that vision-based model based on image and video, as well as a symbolic-based, graph-based model of language are allowing right now to do breakthrough and having a hybrid model working into real application. So it is showing it's a good idea.
And at the level of a brain, like if we do brain imaging on learning, and I'm not sure if we can do exactly what I'm going to ask, but is there a difference? As I said, is there a substantive difference in learning through instruction versus learning through trial and error in terms of the brain activity, like at a kind of a neural architecture standpoint biologically? Is there some difference that is observed or theorized between when we learn by instruction, which is kind of more similar, analogous to hard coding or rules-based system, and learning through trial and error, which is on the other end of the spectrum, like closer to RL? What is the biological difference there, and is there anything we can learn from that in technology sciences?
Yeah. So when you learn something like by instruction or trial of error, you're actually using a lot of different cognitive modules. So you're using your memory, the knowledge you have, but you're also using short-term memory or working memory, because you need to hold what you just learned and so on. So there's suddenly there's a lot of modules and part of the brain that come into place. So what is difficult to disentangle, certainly in a human fMRI study, are the correlating factors. Because if you have two tasks, two ways to learn, but one require more working memory, more effort, then you have the frontal part, the prefrontal part that is responding a lot. And if you're going more into your thoughts or imagining the process, this is another collection of area close to the hippocampus, the retrosplenial cortex. So what we see are differences of what are the modules coming into place, but they are not necessarily at the core of what is driving our internal way to learn. There might be correlation, but we do see differences.
It'd be interesting, you know, thinking about those different parts of the brain that get activated for different types of thing, whether it's like emotional reasoning versus more analytical reasoning. Mm-hmm. It'd be interesting to think about, you know, a hybrid AI system that does that based on the type of task directs the analysis, if you will, to a different type of like structure, like that is tailored for that, you know, rather than trying to. I think we often end up in a bit of a one-size-fits-all approach or a fragmented approach where, okay, a one-size-fits-all tries to do things that it's not really well designed to do. A fragmented approach says, okay, we have all of these different types of AI models that do different things, but they don't necessarily talk to each other in any given setting. You know, and it'd be interesting to think about kind of this next level of artificial intelligence in terms of directing whatever would be analogous to how we direct things to different parts of our brain to do different types of work, you know, not just a different task, but a totally different type of work, emotional versus analytical, and, you know, long-term memory versus short-term memory. And those are all at our disposal. And mm-hmm. somehow we're able to do it on a diet of apples and granola, whereas our AI systems require massive amounts of energy. And so there's something architecturally from a neuroscience standpoint that is just a deep mystery and a fascinating one. That we're still, like, I don't even think we're even scratching the surface yet, it seems.
Yeah, you're so right on the point, Mark. Yeah, there is a solution to artificial general intelligence, or just general intelligence, again, the human brain. And there's a way the different part of the brain works, so we have a coherent behavior. The field of computational neuroscience is looking at the question you just asked. That's a field of neuroscientists who also work with deep learning methods, symbolic approach, and so on, to see to be inspired by the module of the brain working together and how this can give a richer architecture or different architecture. One of the things that is close to the research we do in my lab, looking at the human brain when we do things or hear or see, is actually we work in time. And actually it's pretty slow, 1, 2, 3 seconds, even 100 milliseconds. So what we do see both in animal work and human work is the fact that the module, they come responding over time. So there is a time factor in how the various pieces and part of the brain communicate. That is not something that the artificial intelligence system right now are either implemented or looking at. Maybe they will not need to do this, but certainly timing when things are put together is something very important for the biological system.
I was going to wrap us up, but now that you brought that up, I have to ask about.
What did I say?
I want to ask about, you know, we touched upon projection and imagination. Can you comment at all about dreams as it relates to human intelligence and the neuroscience of dreams at all? Because, you know, we think about time and dreams, and, you know, when we sleep and we go through our REM cycle, you know, there's a lot of study about what's actually happening. There's speculation about, you know, a perception of time in a dream can be different. You know, this was captured in the movie Inception, of course, but there's actual grounding a little bit, and just like our brains maybe for lack of for maybe a simplistic way of putting it, may move at a different speed than when we're awake and conscious. It's like, in terms of our the formation of our intelligence, I'm wondering if you could comment on dreams at all as it relates to neuroscience, creating training data, reasoning and digesting and processing information that we've received during the day. How can we think about that in this context?
Well, you're going to need to ask that question to really an expert. But I might have a sort of related answer. Is certainly right now, or when we go by our day, our system is bombarded by sensory information. I'm hearing my voice, I'm listening to you, I'm looking at the screen, and there is some noise and so on. So while we are awake, you have a system up there that receive all that information and filters or forget about it or take it in. I think actually spend a lot of time to putting a barrier in the filters, okay, particularly when you're outside or it's noisy.
We have to forget. We could never function if we didn't forget.
Exactly. Yeah. Forget, go to backstage. But when you sleep, that is this external information is cut. Okay. So there's something about you're thinking about something and you have this interruption from the world. This is affecting your notion of time, and then you're bored or time goes by fast. So when you're awake, your notion of time is taking into account your own thoughts and what's coming from the external world. When you sleep, there's a cut about the external world. So it's not my area, but this will be a way that we could imagine that the perception out of awake or not awake, or remembering something when you were awake or remembering something when not awake, might have different qualia.
Very good, thank you. Well, one of our participants is recommending we look into David Eagle's work on how brains process time at different states. So we'll do that. Thank you, Thariso.
Thank you.
Well, that's all the time we have for today. It's been wonderful having you along this journey, Ode, and your leadership of the lab is just wonderful and critical on so many levels. So thank you for that. Thank you to the audience. Some of you have been with us for all three sessions: AI we can trust, AI we can scale, and AI we can reason with. We believe these are three important themes for the future of this technology as it relates not only to its scientific development, but to its impact in the real world. We want to remind you we want to invite you actually to join us in learning more about this technology, devoting time and expertise, whatever your expertise is, bringing it to your organization, and also thinking, always staying grounded in, not only what can we do with this technology and others, but what should we do? What's going to help solve problems for other people? What's going to make our societies, our business settings better, and not take us down a path that is unsustainable from an environmental standpoint, or untrustworthy from a standpoint of developing systems that people really rely on. Our website is mitibm.mit.edu. If you want to learn more about our work, we're going to be posting some of our most recent papers being published in the NeurIPS conference coming up very soon. We have works on fairness, works on causality, on neural architecture, all the themes that you've heard on today. They're spaces that are moving very rapidly, and so we have a whole batch of brand new research that we would love to share with you in the upcoming weeks. So as I said, visit our website, follow us on Twitter, and good luck to all of you in all your endeavors to take this technology into your organizations and into society. Thank you, Ode, and thank you, everyone.
Thank you, everyone.